Tonight, we're going to shatter one of the most common misconceptions about our galaxy. When you picture the Milky Way, you probably imagine a beautiful, glowing spiral disk, maybe 100,000 light years across, with bright arms of stars curving outward from a brilliant center. That image is real. But here's what almost nobody realizes. That bright spiral, the entire thing, is only part of the galaxy. The Milky Way extends far, far beyond that disk into a vast ancient structure that most people have never heard of. A structure so large it makes the familiar spiral look like just the bright core of something much grander. And what lives out there in that hidden expanse, ancient stars older than the disk itself, changes everything we thought we knew about our cosmic home. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with what you probably picture when you think of the Milky Way. If you've ever seen an image of our galaxy, and you almost certainly have, you've seen a beautiful spiral. A flat, luminous disk with graceful arms curving outward from a bright central core. Hundreds of billions of stars arranged in this elegant, rotating structure, glowing against the blackness of space. That image is everywhere. In textbooks, in documentaries, on posters in classrooms and science museums around the world. It's one of the most recognizable shapes in all of astronomy. And the image is real. The Milky Way genuinely has a disk. It genuinely has spiral arms. It genuinely has a bright, dense center, packed with stars. But here's what most people never learn. That beautiful spiral, as vast and impressive as it is not the whole galaxy. It's not even the largest component of the galaxy. When you see that iconic spiral image, you're looking at only the most luminous, most photogenic layer of something much, much larger. Something older, dimmer, and profoundly different from the familiar structure everyone knows. Think of it this way. Imagine photographing a great city from an airplane at night. You'd capture the lit streets, the glowing buildings, the bright downtown core. The photograph would be perfectly accurate. Those lights are real. But the city doesn't end where the lights fade. Beyond the brilliant downtown, there are suburbs, parks, quiet neighborhoods stretching far into the surrounding darkness. If you looked at that night photograph and assumed the city ended at the last visible streetlight, you'd massively underestimate the true size of the place. That's essentially what happens with the Milky Way. The bright spiral disk is like the city's downtown, brilliant and impossible to miss. But the galaxy extends far beyond that glowing structure into regions so sparse and dim that they don't appear in almost any image you've ever seen. And these hidden regions, this vast structure enveloping the familiar spiral, changes what the Milky Way actually is, in ways that most people have never been told. But before we explore what lies beyond the disk, we need to understand the disk itself. Because to appreciate just how much of the galaxy is hidden from our usual picture, you first need to understand exactly what you're seeing when you look at that famous spiral. Let's begin with what you can observe with your own eyes. If you've ever been somewhere truly dark, far from city lights, far from highways and buildings, and all the artificial glow of modern civilization, you've probably seen the Milky Way stretching across the night sky. Not as a spiral, because you can't see the spiral shape from inside it, any more than you can see the shape of a forest while standing among the trees. Instead, You see a pale, glowing band of light arching from horizon to horizon. This band has been visible to every human who has ever lived. Ancient cultures looked up at it and wondered. The Greeks believed it was milk spilled across the heavens by the goddess Hera, which is actually where the name Milky Way comes from. The Chinese called it the Silver River. Indigenous Australian cultures saw dark patches within the band as shapes and figures, creating constellations from the dark spaces between stars rather than from the stars themselves. Across every continent, every era, every civilization, that band of light was a constant presence in the sky, mysterious and unexplained. For thousands of years, people had no idea what this glowing band actually was. It wasn't until Galileo pointed one of the first astronomical telescopes at it in 1610 that the truth began to emerge. The band of light was made of individual stars, countless stars, far too many and far too faint to distinguish with the naked eye, their light blending together into that soft, milky glow. What you're seeing when you look at the Milky Way in the night sky is the disk of our galaxy viewed from the inside. You're embedded within a flat structure, so when you look along the plane of that structure, you're gazing through the greatest concentration of stars. That's where the glow comes from. Billions of distant stars overlapping, their light merging into a continuous stream of brightness. When you look above or below the disk's plane, you're looking through fewer stars, out toward the emptier regions beyond the disk, and so the sky appears darker. The band of light is the disk, seen edge on from within, wrapping around us in every direction. And what a disk it is! The Milky Way's disk stretches roughly 100,000 light-years from one side to the other. That's a distance so vast that light itself, traveling at about 300,000 kilometers per second, the fastest speed anything can achieve in the universe, takes 100,000 years to cross it. Let me put that number in perspective. Modern humans as a species have existed for about 300,000 years. If a beam of light had left one edge of the Milky Way's disk the day the very first modern humans appeared on Earth, that light would have traveled only about 3 times the disk's width by now. It would still be well within the wider neighborhood of our galaxy. The disk isn't just large by human standards. It's large by the standards of the universe. Most galaxies in the cosmos are smaller than this. The Milky Way's disk alone makes it one of the larger galaxies in existence, in the top 5% by size. That's before we even begin to talk about what lies beyond the disk. Inside this enormous structure, somewhere between 100 billion and 400 billion stars are distributed across the spiral arms and the spaces between them. The exact number is difficult to determine because counting stars inside a galaxy you're part of is a remarkably tricky problem. Dust clouds block our view in many directions, absorbing and scattering starlight so that entire regions of the galaxy are hidden from us in visible light. Dim, small stars, which are actually the most common type, are hard to detect even with powerful telescopes. And the galaxy is so large that we simply can't see all of it from our vantage point, embedded in the disk and offset from the center. But the best estimates place the total number of stars somewhere around 200 to 400 billion. Each one of those stars is a sun. Some are far larger than ours, blazing with tens of thousands of times our star's luminosity. Some are far smaller, dim red dwarfs barely visible even from nearby. Some are hotter, some are cooler, some are younger, some are older, but each one is a nuclear furnace, converting hydrogen into helium through fusion and radiating energy into space, just like our own star does every second of every day. Now, here's something that surprises most people when they first learn it. Despite its vast width, the disk is thin. Remarkably, almost absurdly thin compared to how wide it stretches. While the disk spans about 100,000 light-years across, its main visible layer is only about 1,000 to 2,000 light-years thick. Think about that ratio for a moment. If you scaled the disk down to a structure 100 meters wide, it would be only about 1 to 2 meters tall. That's remarkably flat. If you could somehow see the Milky Way from the side, edge on, it would look less like a dinner plate and more like a compact disk. An incredibly thin, flat structure with a slight bulge at the center. In fact, proportionally, the Milky Way's disk is thinner relative to its width than most pancakes you've ever eaten. It's extraordinarily, almost unbelievably flat. The thinness of the disk tells us something important about how it formed. Stars in the disk orbit the galactic center in roughly circular paths, all moving in the same general direction, much like planets orbiting a star. This organized collective motion is what keeps the disk flat. It's the same physics that flattens the solar system. When a cloud of material collapses under gravity while rotating, conservation of angular momentum forces it into a disk shape. Material moving in random directions collides, loses energy, and settles into the plane of rotation. The faster the spin, the thinner the disk becomes. And the Milky Way's disk is very thin indeed, which tells us the material from which it formed had a great deal of organized rotation. Everything in the disk is moving together, orbiting in the same direction, maintaining this incredible flatness across 100,000 light-years. But the disk isn't a uniform sheet. It has structure, rich and complex structure. The most striking features are the spiral arms, those great curving rivers of stars, gas and dust that give spiral galaxies their distinctive and beautiful appearance. The Milky Way has several major spiral arms, including the Perseus arm, the Sagittarius arm, and the Scutum Centaurus arm, along with smaller structures called spurs that connect them. Our Sun sits in one of these smaller features, called the Orion Spur, a relatively minor arm between the larger Sagittarius and Perseus arms. These spiral arms aren't solid walls of stars moving together through space. Instead, they're what astronomers call density waves, regions where gas and stars are temporarily compressed as they orbit the galactic center. Think of them like traffic jams on a circular highway. The jam stays in roughly the same place on the road, even though individual cars constantly enter it from behind and exit it at the front. Similarly, spiral arms maintain their overall shape and position, even though individual stars pass in and out of them over tens of millions of years. A star might spend a few million years inside a spiral arm, then drift out into the space between arms, then eventually enter the next arm millions of years later. The arms are patterns, not permanent collections of the same stars. The arms appear especially bright because they contain large concentrations of gas and dust. When gas gets compressed within a spiral arm, dense pockets of it can collapse under their own gravity and form new stars. Many of these newborn stars are massive, hot, and incredibly luminous, blazing with brilliant blue-white light that makes the spiral arms stand out vividly against the rest of the disk. These massive stars burn through their nuclear fuel at a ferocious rate, living for only a few million years before exploding as supernovae. By the time they die, they haven't drifted far from where they were born, so they remain within the spiral arm that created them. This is why the spiral arms glow so brightly. They're the nurseries of the galaxy, the places where new stars are constantly being born, lighting up the arms with their youthful brilliance, while the older, dimmer stars between the arms are harder to see. Our own sun sits in the Orion Spur, about 26,000 light years from the galactic center, roughly halfway between the center and the outer edge of the disk. We're in a relatively quiet stretch of the galaxy, not in one of the densest star-forming regions, not in the chaotic, radiation-heavy environment near the galactic core, but in a calm, stable neighborhood where stars are spread far enough apart that a planetary system can develop and persist for billions of years without being disrupted by nearby supernova explosions or gravitational encounters with passing stars. This quiet position might be one of the reasons life was able to arise and survive on Earth. A planet closer to the galactic center, where stars are packed more densely and supernovae are more frequent, might have been sterilized by radiation long before complex life could develop. The Sun orbits the center of the galaxy at a speed of about 230 kilometers per second. That sounds incredibly fast, and it is. At that velocity, you could travel from Earth to the Moon in under half an hour. You could cross the entire United States in about 3 minutes. But the galaxy is so enormous that even at this tremendous speed, it takes the Sun roughly 225 million to 250 million years to complete a single orbit around the galactic center. This period is sometimes called a galactic year or a cosmic year. The last time the Sun was at approximately this same point in its orbit, dinosaurs were just beginning to appear on Earth. The first dinosaurs evolved about 230 million years ago, roughly one galactic year in the past. Everything that has happened since then, the entire age of dinosaurs, their extinction 66 million years ago, the rise of mammals, the evolution of primates, the emergence of humans, the invention of agriculture, the building of civilizations, all of recorded human history, all of it has occurred during a single orbit of the Sun around the galaxy. And the Sun has completed only about 20 such orbits in its entire 4.5 billion year lifetime. The galaxy operates on timescales that dwarf anything in human experience. At the very heart of the disk sits the central bulge. This is a dense, roughly spherical concentration of stars at the center of the galaxy, extending about 10,000 light-years across. Unlike the disk, which is filled with both young and old stars, the bulge contains primarily older stars, many of them billions of years old, packed far more tightly than stars in our neighborhood. If you could somehow stand on a planet near the galactic center, your night sky would be utterly unlike anything visible from Earth. Instead of a few thousand stars visible to the naked eye, you'd see tens of thousands, perhaps hundreds of thousands of brilliant stars in every direction. The sky would glow with an almost continuous blanket of starlight. True darkness as we know it on Earth might barely exist there. Living near the galactic center would be like living inside a jewel box, surrounded by light in every direction. The bulge also contains a bar, a long, rectangular structure of stars cutting through the center of the galaxy. This bar extends roughly 27,000 light-years from end to end, and it's why the Milky Way is classified as a barred spiral galaxy rather than a simple spiral. Barred spirals are actually quite common among spiral galaxies. perhaps 2/3 of all spirals have central bars. The bar is created by stars on elongated orbits that carry them back and forth through the galactic center, creating this stretched, rectangular shape over time. The spiral arms of the Milky Way extend from the ends of this bar, curving outward into the wider disk. And at the absolute center of everything, at the core of the bulge, at the heart of the bar, sits a supermassive black hole. Sagittarius A star, as astronomers call it, has a mass of about 4 million times the mass of our Sun. All of that mass is compressed into a region smaller than the orbit of Mercury around our star. Despite its enormous mass, Sagittarius A weak star is relatively quiet right now. It's not actively consuming large amounts of surrounding material. It's not producing the enormous jets of matter and energy that some supermassive black holes in other galaxies produce. Jets that can extend for thousands of light years into intergalactic space. It's sitting there, a dark, massive anchor at the very center of the galaxy, shaping the orbits of the nearest stars through its immense gravitational pull. Stars orbiting close to Sagittarius E star move at astonishing speeds. One star, known as S2, completes an orbit around the black hole in just 16 years, reaching velocities near 3% of the speed of light at its closest approach. That's roughly 7,600 kilometers per second. By comparison, our Sun plods along at a leisurely 230 kilometers per second in its much larger orbit around the galactic center. The staggering difference in speed gives you a visceral sense of how much stronger gravity becomes near the center. Near Sagittarius I star, the galaxy is violent, extreme, and chaotic. Out where we live, 26,000 light years away, things are calm, stable, and quiet. So that's the disk. A thin, flat structure roughly 100,000 light years across and 1 to 2,000 light years thick, containing hundreds of billions of stars, arranged in spiral arms around a dense central bulge with a supermassive black hole at the core. It's beautiful, it's vast, and it's real. This is the Milky Way that most people know. The structure shown in every diagram, every artist's rendering, every popular science illustration, but it's not the whole galaxy. For a surprisingly long time, astronomers thought the disk was essentially everything there was. In the early 1900s, many scientists believed the Milky Way was the entire universe. There was intense debate about whether the faint, fuzzy patches of light visible through telescopes, called nebulae at the time, were clouds of gas within our galaxy or entire separate galaxies far beyond it. This question was so contentious that in 1920, the National Academy of Sciences in the United States organized a formal public debate between two prominent astronomers, Harlow Shapley and Hilbert Curtis. Shapley argued that the Milky Way was the entire universe, and that these nebulae were simply features within it. Curtis argued that at least some of the nebulae were separate galaxies, what he called island universes, located at immense distances beyond the Milky Way's boundaries. The debate wasn't resolved that night. It took several more years. In 1924 and 1925, Edwin Hubble, using the powerful 100-inch telescope at Mount Wilson Observatory in California, identified individual stars within the Andromeda Nebula. By measuring the brightness of a type of pulsating star called a Cepheid variable, whose intrinsic luminosity is related to the period of its pulsation in a predictable way, Hubble calculated the distance to Andromeda and showed conclusively that it was far too distant to be inside the Milky Way. It was a separate galaxy entirely, roughly 2.5 million light years away. A completely independent system of billions of stars, comparable in scale to our own galaxy but separated from us by an almost incomprehensible gulf of empty space. This discovery shattered the old picture. The Milky Way wasn't everything. It was one galaxy among many. And suddenly, understanding the true structure and boundaries of our own galaxy became a far more urgent and important question. If the Milky Way isn't all there is, then what exactly is it? Where does it start and end? How far does it really extend? Answering those questions took decades of painstaking work. Astronomers gradually mapped the disk, measuring distances to stars and gas clouds, tracing the positions and shapes of the spiral arms, determining where the sun sat within the overall structure. By the mid-20th century, the picture of the bright disk was well established. The Milky Way was understood to be a large, barred spiral galaxy, roughly 100,000 light-years across, containing hundreds of billions of stars, with our sun located about 2/3 of the way out from the center in a minor spiral arm. But even as this neat picture came into focus, there were stubborn hints that the disk was not the whole story. Some stars simply didn't behave the way disk stars should. They moved on strange, highly elongated orbits, plunging far above and below the plane of the disk, rather than circling neatly within it. Their chemical compositions were strikingly different from typical disk stars. They contained far fewer heavy elements like iron, carbon, and oxygen, elements that astronomers call metals, suggesting these odd stars had formed in an earlier era of the universe's history, before many generations of stars had lived and died, and enriched the surrounding gas with heavier atoms forged in their cores and scattered by their explosions. These weren't wayward disk stars on unusual paths. They belonged to something else entirely. Something older, more chaotic, and potentially much larger than the organized spiral. And then there were the globular clusters, dense, spherical collections of hundreds of thousands of ancient stars, each cluster a tightly bound city of suns. Globular clusters did not sit within the disk. They orbited far above and below it, tracing enormous elliptical paths that carried them tens of thousands of light years from the galactic plane. Some of these clusters contained stars that formed more than 13 billion years ago, when the universe itself was less than 1 billion years old. These were among the most ancient objects in the entire galaxy. Whatever structure they belonged to, it was far older and far more extensive than the bright, youthful disk. In fact, it was Harlow Shapley, the same astronomer who had once argued the Milky Way was the entire universe, who first used globular clusters to reveal the galaxy's larger structure. In 1918 and 1919, Shapley carefully mapped the positions of globular clusters across the sky and noticed something striking. They weren't distributed evenly. They clustered heavily toward one region of the sky, centered on the constellation Sagittarius. Shapley reasoned that the globular clusters were orbiting the center of the galaxy, and since they were concentrated toward Sagittarius, the galactic center must lie in that direction. He was right. This observation not only pinpointed the direction and approximate distance of the galactic center, but also proved that the sun was far from that center, orbiting out in the galactic suburbs rather than sitting at any privileged central position. And more importantly for our story tonight, Shapley's work revealed that the galaxy had a component extending far beyond the disk. The globular clusters traced out a roughly spherical distribution around the galactic center, reaching to distances vastly greater than the thickness of the disk. The galaxy was not merely a flat spiral, it had depth, enormous depth, in a direction the disk could not account for. This was the first real evidence of what astronomers would come to call the stellar halo, a vast, roughly spherical cloud of ancient stars and star clusters enveloping the familiar bright disk on all sides. The disk was spectacular, certainly, but it was embedded inside something much, much larger, like a glowing core wrapped in an enormous, dim shell that extended far beyond the bright structure in every direction. For decades after this discovery, the stellar halo remained a background detail in most descriptions of the Milky Way. Textbooks mentioned it, but usually briefly, treating it as a minor component containing only a small fraction of the galaxy's total stars. The disk was the star of the show. The spiral arms, the star-forming regions, the brilliant central bulge, the supermassive black hole, those were the features that made it into the illustrations and the documentaries. The halo was treated as an afterthought, a dim scattering of old stars that happened to surround the real galaxy without contributing much of significance. But that view was deeply, profoundly wrong. Because the stellar halo is not just a faint dusting of old stars around the edges of the disk. It extends to distances that make the disk look compact by comparison. While the bright disk stretches about 100,000 light years from edge to edge, the stellar halo reaches outward to at least 300,000 light years from the galactic center, and possibly much farther. That means the halo extends roughly 3 times beyond the edge of the visible disk in every direction. The volume of space it occupies is vastly, overwhelmingly larger than the volume of the disk. The disk, for all its beauty and brilliance, sits inside the halo like a coin lying flat at the center of a large, dim room. And what fills that enormous volume, what those ancient stars and clusters and strange orbital paths tell us about how the galaxy formed and how far it truly reaches, is a story that transforms the Milky Way from a flat, familiar spiral into something far grander, far more ancient and far more surprising than the picture most people carry in their heads. The bright disk is where most of the galaxy's visible action takes place. It's where new stars are born, where planets form, where life as we know it emerged on at least one small rocky world orbiting an ordinary yellow star. But the disk is not the whole galaxy. It's not even the outermost reach of the galaxy's stars. When you look at that famous spiral image, you're seeing the most visible part of a structure that stretches far beyond the frame. The Milky Way doesn't end where the spiral arms fade from view. It keeps going outward, upward, downward, into regions so sparse that individual stars are separated by enormous gulfs of empty space, into a realm of ancient ghostly light that has been there since before the disk itself existed. And that realm, that enormous invisible structure surrounding the bright disk we all know, is where we're heading next. The stellar halo is one of the most extraordinary and least understood parts of the Milky Way. Most people have never heard of it. It doesn't appear in most popular illustrations of the galaxy. It's not bright enough to photograph easily, not dramatic enough to make headlines, not compact enough to fit neatly into the simple picture of a spiral galaxy that we all carry in our minds. And yet, the stellar halo is arguably the most important structure for understanding what the Milky Way truly is, how far it actually extends, and how it came to exist in the first place. If the bright disk is the galaxy's present, the stellar halo is its past. And that past stretches back to a time when the universe itself was barely recognizable. So what exactly is the stellar halo? Let's break it down in clear physical terms, because this is a structure that most descriptions gloss over far too quickly. The stellar halo is a vast, roughly spherical cloud of stars that surrounds the disk on all sides. Not a ring, not a band. A sphere, or more accurately, a slightly flattened ellipsoid, extending outward from the galactic center in every direction, above the disk, below it, and far beyond its edges. If the disk is a flat plate lying horizontally, the stellar halo is the enormous room that plate sits inside. It extends above, below, and far beyond the plate's rim, filling a volume of space that makes the disk look almost compact by comparison. The stars in this halo are fundamentally different from the stars in the disk. Different in age, different in composition, different in how they move, different in what they tell us about the galaxy's history. Understanding these differences is the key to understanding why the halo matters so much. Let's start with how they move, because this is perhaps the most dramatic distinction. Stars in the disk orbit the galactic center in a remarkably organized fashion. They move on roughly circular paths, all traveling in the same general direction, all staying close to the plane of the disk. It's orderly, like cars on a circular highway, all driving the same way. This collective, organized motion is what keeps the disk flat and thin. Everything is rotating together in a vast, coordinated spin. Halo stars do not behave this way at all. They move on wildly elongated, elliptical orbits that carry them far above and below the disk plane. Some plunge down through the disk from enormous heights, pass through it, and then soar upward on the other side before falling back again. Others orbit in directions completely different from the disk's rotation. Some even orbit in the opposite direction, moving against the flow of the disk entirely. If disk stars are like cars all driving the same way on a highway, halo stars are like birds flying in every direction through a vast open sky. There's no common direction, no shared plane of motion. Each halo star follows its own individual path, set by the gravitational pull of the galaxy as a whole, but not confined to any particular plane or direction. This chaotic motion is not random in the mathematical sense. Each star's orbit is determined by the gravitational field of the galaxy, so the orbits are predictable if you know the star's position and velocity. But taken as a population, halo stars show no preference of any particular direction of motion. They don't rotate around the galactic center in any organized way. Some go clockwise, some go counterclockwise, some go nearly straight up and down. This lack of organized rotation is fundamentally different from the disk, and it tells us something crucial about how the halo formed. The disk formed from a cloud of gas that was spinning, and that spin forced the gas into a flat, rotating plane. The halo did not form this way. Its stars came from a messier, more chaotic process, one that didn't produce any preferred direction of rotation. We'll explore exactly what that process was later, but for now, the key point is this. The way halo stars move tells us they belong to a completely different structural component of the galaxy than the disk. They're not wayward disk stars. They're members of a separate, older population. Now let's talk about composition, because this is where the story gets even more revealing. Stars are made of gas, primarily hydrogen and helium, but they also contain trace amounts of heavier elements, things like carbon, oxygen, iron, silicon, and dozens of other elements that astronomers, somewhat confusingly, refer to collectively as metals. In astronomical jargon, anything heavier than helium is a metal. This includes things like oxygen and carbon, which a chemist would never call metals. But astronomers use the term loosely to mean any heavy element. Here's why this matters. The very first stars that formed in the universe, stars born just a few 100 million years after the Big Bang, formed from gas that was almost pure hydrogen and helium. Those were the only elements the Big Bang produced in significant quantities. There were essentially no heavy elements available, no carbon, no oxygen, no iron. Those first stars were made of the simplest, lightest stuff in existence. When those first stars died, many of them exploded as supernovae, scattering newly forged heavy elements into the surrounding gas. The next generation of stars formed from gas that was slightly enriched with these heavier atoms. When those second generation stars died, they scattered even more heavy elements, enriching the gas further. Each successive generation of stars formed from gas that contained more and more heavy elements, forged in the cores and explosions of previous stellar generations. This means that a star's chemical composition is like a timestamp. Stars with very few heavy elements formed early, from gas that hadn't been enriched much yet. Stars with more heavy elements formed later, from gas that had been processed through multiple generations of stellar birth and death. The iron to hydrogen ratio in a star's atmosphere is one of the most commonly used indicators of this enrichment history. A star with a very low iron content relative to hydrogen formed from nearly pristine gas that had been processed through very few previous generations of stars. And here's the remarkable thing about halo stars. They are among the most metal-poor stars in the entire galaxy. Some halo stars contain less than 1% of the iron found in the Sun. Some contain less than 1/10 of 1%. A few extreme examples contain less than 100,000th of the Sun's iron abundance. These are stars that formed from gas so pristine, so unenriched, that it was almost indistinguishable from the raw material left over from the Big Bang itself. This extreme metal poverty tells us that halo stars are ancient. Profoundly, almost incomprehensibly ancient. They formed in the earliest epochs of the universe, long before the Milky Way's disk existed, long before the spiral arms appeared, long before the Sun or Earth or anything we're familiar with had come into being. Many halo stars are estimated to be 12 to 13 billion years old. The universe itself is only about 13.8 billion years old. These stars formed when the cosmos was less than 1 billion years old, when the universe was still in its infancy, still assembling its first galaxies from the primordial gas left over from the Big Bang. Let me put that age in perspective. Our Sun is about 4.5 billion years old. It's a middle-aged star, roughly halfway through its expected 10 billion year lifespan. The oldest halo stars are nearly 3 times the age of the Sun. They were already ancient, already billions of years old, when the Sun and Earth first formed, from a collapsing cloud of gas and dust 4.5 billion years ago. These stars have been burning steadily since an era when the Milky Way's disk didn't exist yet, when the galaxy was still assembling itself from smaller fragments, when the universe looked completely different from how it looks today. If these stars could somehow tell their story, they would describe a cosmos without spiral galaxies, without most of the structure we see today, a younger, hotter, denser, more chaotic universe, still in the process of figuring out what it was going to become. The halo also contains some of the most ancient and fascinating objects in the galaxy. Globular clusters. These are dense, spherical collections of stars, tightly bound together by their mutual gravity into compact, nearly perfect spheres of light. A typical globular cluster contains somewhere between 100,000 and a million stars, all packed into a region maybe 100 to 200 light years across. Some are larger, some are smaller, but they're all remarkably dense compared to the regions of the galaxy where our sun lives. Near the center of a globular cluster, stars can be separated by only a fraction of a light year, dozens of times closer together than the stars in our solar neighborhood. If you could stand on a planet near the center of a globular cluster, your night sky would be breathtaking, packed with thousands of brilliant stars, some bright enough to cast shadows at night. A sky so crowded with light that true darkness would never fully arrive. The Milky Way has about 150 known globular clusters, though the actual number might be somewhat higher since some could be hidden behind the disk's dust. These clusters are scattered throughout the halo, orbiting the galactic center on the same kind of elongated, chaotic paths as individual halo stars. Some orbit relatively close to the galactic center, plunging through the disk on each pass. Others swing out to enormous distances, spending most of their time far from the disk in the sparse outer reaches of the halo. 47 Tucanae, one of the brightest and most massive globular clusters, lies about 13,000 light years from Earth. M13, in the constellation Hercules, is roughly 22,000 light years from us. But some globular clusters orbit at distances of 100,000 light years or more from the center, far beyond the edge of the visible disk, out in the remote depths of the halo, where stars are incredibly scarce. Omega Centauri, also known as NGC 5139, is the largest and most massive globular cluster associated with the Milky Way. It contains roughly 10 million stars, far more than a typical globular cluster. It has a diameter of about 150 light years. Some astronomers believe Omega Centauri is not actually a true globular cluster at all, but rather the stripped core of a small galaxy that was consumed by the Milky Way long ago. If so, its stars were not originally part of our galaxy. They were stolen from another galaxy entirely, captured and absorbed as the Milky Way grew by cannibalizing its smaller neighbors. This idea connects directly to how the halo was built, a process we'll explore in depth very soon. The ages of globular clusters reinforce the picture of the halo as an ancient structure. Many globular clusters are estimated to be between 11 and 13 billion years old. Some are among the oldest objects in the entire universe that we can directly observe and study. They formed when the cosmos was young, when the first structures were still assembling, when the Milky Way existed only as a loose collection of small, merging proto-galaxies. These clusters have survived for over 13 billion years, outlasting everything around them, orbiting the galaxy steadily while the disk formed, the spiral arms appeared, the sun was born, life arose on Earth, and humans eventually built telescopes powerful enough to study them. Now, let's talk about how far the stellar halo actually extends, because this is where the true scale of the galaxy starts to reveal itself. The bright disk of the Milky Way, as we established earlier, stretches roughly 100,000 light years across. When most people think of the galaxy's size, this is the number they have in mind: 100,000 light years. It's a figure quoted in virtually every description of the Milky Way. It's on posters and infographics and the opening slides of countless astronomy presentations, and it's correct as a measurement of the disk. But the galaxy does not end where the disk ends. The stellar halo extends far beyond the disk's edge. Current observations suggest that halo stars can be found out to distances of at least 300,000 light-years from the galactic center. Some studies have detected halo stars at distances approaching 400,000 light-years, and a few observations have hinted at stellar populations even farther out than that. Though the evidence at the most extreme distances becomes uncertain because the stars are so sparse and so faint that confirming their membership in the Milky Way's halo, rather than being foreground objects or members of neighboring satellite galaxies, becomes extremely difficult. Let's think about what this means. The disk stretches about 50,000 light-years from the center to its outer edge in any direction along the plane. The halo extends at least 300,000 light-years from the center. That means the halo reaches roughly 6 times farther from the galactic center than the disk does. The structure most people think of as the entire galaxy, the beautiful spiral with its bright arms and glowing center, fits inside the stellar halo many times over. If you could see the disk and the halo together, with the halo made somehow visible, the disk would look like a small, flat, bright coin sitting at the center of an enormous, dim, spherical cloud. The coin would be striking and beautiful, certainly, but it would be dwarfed by the structure surrounding it. To make this even more tangible, think about where the sun sits. We're located about 26,000 light-years from the galactic center, inside the disk. The far edge of the disk is roughly another 24,000 light-years beyond us, but the outer reaches of the stellar halo are 300,000 light-years from the center. That's about 274,000 light-years beyond our position. The halo stars at the outermost edge of the galaxy are more than 10 times farther from us than we are from the galactic center. We sit deep inside the galaxy, surrounded on all sides by this enormous spherical structure, most of which lies far, far beyond the disk we call home. Here's an analogy that might help. Imagine you live in a small town at the center of a large county. The town has streets and buildings and lights, clearly visible from any direction. That's the disk. Now imagine the county extends far beyond the town in every direction. Quiet farmland and open space stretch into distant borders you can barely see. The county is much larger than the town, but because the town is where all the action is, where the lights are, where people gather, it's easy to mistake the town for the whole county. The stellar halo is like the rest of the county. Vast, quiet, sparsely populated, but undeniably part of the same entity. But here's what makes this even more striking. Despite its enormous volume, the stellar halo contains only a tiny fraction of the galaxy's total stars. Estimates vary, but the halo is thought to contain only about 1 to 2% of the Milky Way's stellar population. Maybe 2 billion to 8 billion stars, spread across a volume many times larger than the disk. Compare that to the disk, which contains the vast majority of the galaxy's hundreds of billions of stars packed into a thin, flat structure. The halo has far fewer stars than the disk, but those stars are distributed across a much larger space. This means the halo is incredibly sparse. If the disk is a crowded city packed with millions of residents, the halo is an enormous wilderness with scattered homesteads, separated by vast tracts of empty land. The density of stars in the halo drops dramatically as you move outward from the galactic center. Near the inner halo, within maybe 30,000 light-years of the center, stars are still relatively detectable, though far less dense than in the disk. But in the outer halo, Beyond 100,000 light years, stars become astonishingly rare. You could travel through enormous volumes of space and encounter nothing. Just darkness. Just the faint, distant glow of the disk behind you, and the even fainter glow of distant galaxies ahead. And yet, occasional stars do exist out there. Ancient suns burning quietly in the void, members of the Milky Way, despite being farther from the galactic center than many neighboring dwarf galaxies. To truly grasp what the halo feels like, imagine you could somehow leave the disk and travel outward into it. You begin near the sun, surrounded by the familiar stars of our neighborhood. As you rise above the plane of the disk, the stars around you begin to thin. The dense river of starlight that forms the Milky Way's band across the sky flattens beneath you, becoming a luminous sheet stretching to the horizon in every direction. You're above the disk now, looking down at it like a pilot looking down at a city at night. The spiral arms are laid out below you, rivers of light curving gracefully around the brilliant central core. It's one of the most beautiful sights imaginable, but you keep going. Upward, outward, farther from the disk. The sheet of light below you grows smaller. Not dimmer exactly, but more compact, shrinking against the surrounding darkness as you gain distance. The stars around you become fewer and fewer. At first, you pass through the inner halo, where occasional old stars drift past, reddish and dim, each one ancient beyond reckoning. A globular cluster might appear in the distance, a dense, glowing sphere of hundreds of thousands of stars packed tightly together, brilliant against the emptiness. Like a distant lighthouse in an otherwise dark ocean. But as you travel farther, even these encounters become rarer. At 100,000 light years from the center, you pass beyond the edge of the disk entirely. The bright spiral is now a distant structure below and behind you, still visible but clearly finite, clearly bounded, a flat, glowing object hanging in the darkness. And the space around you is almost empty. You might travel for thousands of light years without passing a single star. The silence, the darkness, the sheer emptiness would be overwhelming. There is no sound in space, of course, but the visual silence would be just as profound. Nothing but blackness in every direction, punctuated only by the distant smudge of the disk behind you, and the even fainter smudges of other galaxies scattered across the void. And yet, you're still inside the Milky Way. You're still gravitationally bound to our galaxy. The occasional ancient star you pass, dim and reddish, burning through its fuel at a rate so slow it will shine for longer than the current age of the universe, is still a member of the Milky Way. It still orbits the same galactic center, still follows a path determined by the galaxy's gravity, still carries the chemical fingerprints of the ancient gas from which it formed billions of years ago. You're in the Milky Way's outermost reaches, a region so sparse it's nearly indistinguishable from intergalactic space, but it's still the galaxy. The galaxy extends this far. This is how large it truly is. The existence of these incredibly remote halo stars raises a question that most people never think to ask. If the stellar halo is so sparse, so dim, so difficult to see, how did astronomers even discover it? How do you find a scattered population of faint, ancient stars spread across a volume hundreds of thousands of light years across? The answer involves some remarkably clever astronomical detective work. One of the earliest clues came from a type of star called an RR Lyrae variable. These are old, low-mass stars that pulsate, brightening and dimming in a regular, predictable cycle, Like the Cepheid variables that Edwin Hubble used to measure the distance to Andromeda, RR Lyrae stars have a relationship between their pulsation period and their intrinsic luminosity, which means astronomers can calculate exactly how bright they truly are. By comparing this intrinsic brightness to how bright they appear from Earth, astronomers can determine how far away they are. RR Lyrae stars are particularly useful for mapping the halo because they're old, metal-poor stars, exactly the kind of stars the halo contains, and because their distinctive pulsation pattern makes them easy to identify even at great distances. By surveying the sky for RR Lyrae stars and calculating the distances, astronomers were able to trace out the three-dimensional structure of the halo. What they found confirmed and extended the picture that had first emerged from studies of globular clusters. The halo stars formed a roughly spherical distribution around the galactic center, extending far beyond the disk, with their density decreasing smoothly as distance from the center increased. This was not a separate, disconnected structure floating near the Milky Way. It was part of the Milky Way, gravitationally bound to the galaxy, orbiting the same center, but occupying a vastly larger volume of space than the disk. Another crucial tool in the study of the halo has been the identification of what astronomers call blue horizontal branch stars. These are evolved stars that have passed through the red giant phase and settled onto a particular stage of their life cycle where they burn helium in their cores rather than hydrogen. Blue horizontal branch stars are luminous enough to be visible at great distances, and like RR Lyrae stars, they tend to be old and metal poor, making them excellent tracers of halo populations. Surveys targeting these stars have pushed our knowledge of the halo's extent to ever greater distances, revealing stars at 200,000, 300,000, and possibly even farther from the galactic center. But perhaps the most transformative tool for studying the halo arrived much more recently. In 2013, the European Space Agency launched the Gaia spacecraft. Gaia's mission is to create the most detailed three-dimensional map of the Milky Way ever produced, and its results have been nothing short of revolutionary. Gaia has measured the precise positions, distances, and motions of nearly 2 billion stars. This is an almost inconceivable amount of data, a catalogue of stellar positions and velocities so vast and precise that it has transformed every branch of galactic astronomy. For the study of the halo, Gaia has been extraordinary. By measuring not just where halo stars are, but how they're moving, Gaia has revealed the halo's structure in unprecedented detail. It has shown that the halo is not a smooth, featureless cloud of randomly scattered stars. Instead, it's laced with structure, with streams and clumps and shells of stars that trace out the remnants of ancient events. The halo carries scars. It bears the imprints of its own violent history, a history written in the orbits and compositions of its stars, preserved for billions of years like fossils in stone. And this brings us to one of the most stunning revelations about the stellar halo. The halo is not just a static shell of old stars that has existed unchanged since the galaxy's youth. It's a record, a living archaeological site. The halo preserves evidence of events that shaped the Milky Way over its entire 13 billion year history. Because in these sparse outer regions of the galaxy, where stars are few and gravitational interactions are gentle, structures can survive for billions of years. A stream of stars pulled from a consumed dwarf galaxy doesn't dissipate quickly in the halo, the way it would in the crowded, dynamic environment of the disk. Instead, it persists, stretching across thousands or even hundreds of thousands of light years. A ghostly trail marking where a smaller galaxy was destroyed by the Milky Way's gravity long ago. This is what makes the halo so important. It's not just big, it's not just ancient, it's a library, a vast three-dimensional archive of the galaxy's formation history, written in the positions, motions, and chemical compositions of its stars. Every stream, every clump, every shell of stars in the halo tells a story about a smaller galaxy that was captured and consumed by the Milky Way. And when astronomers read these stories, they discover something astonishing about how our galaxy grew. The Milky Way didn't form in isolation. It didn't simply condense from a single collapsing cloud of gas. It grew, at least in part, by consuming other galaxies. Smaller systems fell into its gravitational well, were stretched and torn apart by tidal forces, and their stars were scattered across the halo, where they remain today as ghostly remnants of galaxies that no longer exist as independent entities. The halo, then, is not just the largest visible structure in the Milky Way by volume. It's a graveyard, a vast spherical cemetery of consumed galaxies, their stars still orbiting, still carrying the chemical fingerprints and orbital signatures of their lost homeworlds, even billions of years after those homeworlds were destroyed. And the scale of this graveyard, the sheer extent of the halo, tells us that the Milky Way's true reach, its real gravitational domain, extends far beyond the bright spiral disk that everyone knows and pictures. When you see that iconic image of a beautiful spiral galaxy, you're seeing the part that glows, the part where new stars are being born, where gas and dust catch the light, where the galaxy is most visible and most photogenic. But the full galaxy, the complete gravitational entity that we call the Milky Way, extends vastly farther into space, into a dim, ancient realm where scattered metal-poor stars orbit on wild path through an enormous volume that dwarfs the disk in every dimension except sheer star count. The disk is where the Milky Way lives today. It's where the action is, where stars are forming, where planets are orbiting, where life emerged. But the halo is where the Milky Way's story began. Its stars carry memories of a younger, more violent era, an era of mergers and collisions and galactic cannibalism that built the galaxy we inhabit. And the fact that those stars extend to distances of 300,000 light years or more from the galactic center means the Milky Way is not 100,000 light year wide spiral. It's a structure at least several 100,000 light years across when measured from one end of its stellar halo to the other. That's the true scale of the galaxy. Not the disk alone, not the bright arms, but the entire structure, disk and halo together, stretching far beyond the familiar image into the ancient darkness that surrounds it. And what we've found within that darkness, the streams and remnants and consumed galaxies hiding in the halo's depths, reveals a history more dramatic and more violent than the calm, orderly spiral would ever suggest. The stellar halo surrounds the Milky Way like an enormous, ancient shroud. We know it's there. We know it's vast. We know its stars are among the oldest in the galaxy. But understanding what the halo is raises an even more compelling question. How did it get there? Where did those ancient, metal-poor stars come from? How did they end up on their wild, chaotic orbits, scattered across a volume hundreds of thousands of light years wide? For a long time, astronomers assumed the answer was simple. The halo was thought to be a relic of the galaxy's original formation. The idea was that when the Milky Way first began to collapse from a massive cloud of primordial gas billions of years ago, the earlier stars formed before the gas had settled into a flat, rotating disk. These first stars would have been scattered throughout the collapsing cloud, orbiting in all directions, and when the gas eventually flattened into the disk under the influence of rotation, those early stars would have been left behind in a spherical distribution around the center. The halo in this picture was a fossil of the galaxy's birth. The first stars formed before the disk existed, frozen in their original orbits for eternity. This picture was elegant, it was simple, and it turned out to be incomplete. Because over the last few decades, astronomers have discovered something extraordinary. The halo is not merely a relic of the galaxy's initial formation. Much of it was built later, through a process far more dramatic and violent than anyone originally imagined. The Milky Way constructed a significant portion of its stellar halo by tearing apart and devouring smaller galaxies. This process is called galactic cannibalism, and it's exactly as dramatic as it sounds. When a smaller galaxy, a dwarf galaxy containing perhaps a few billion stars or even fewer, wanders too close to a much larger galaxy like the Milky Way, the larger galaxy's gravity begins to pull on it. But gravity doesn't pull equally on all parts of the smaller galaxy. The side of the dwarf galaxy closer to the Milky Way feels a stronger gravitational tug than the far side, because gravity weakens with distance. This difference in gravitational pull across the body of the smaller galaxy is called a tidal force, and over time, it stretches the dwarf galaxy like taffy. Imagine holding a ball of soft clay near a powerful magnet. The side of the clay closer to the magnet would be pulled more strongly than the far side. Over time, the clay would stretch into an elongated shape. If the pull was strong enough and sustained long enough, the clay would eventually be drawn into a long, thin strand. That's essentially what happens to a dwarf galaxy caught in the Milky Way's gravitational field. The tidal forces stretch it, distort it, and eventually pull it apart entirely. Stars are ripped away from the dwarf galaxy, streaming out ahead of and behind the disrupted system in long, thin arcs called tidal streams or stellar streams. These streams are among the most beautiful and haunting structures in the galaxy. They're rivers of stars, stretched across tens of thousands or even hundreds of thousands of light years, tracing out the orbital path of the galaxy that was destroyed. Each stream is a fossil, a ghostly remnant of a galaxy that once existed as an independent entity with its own stars, its own structure, its own history, now reduced to a long, thin thread of stars winding through the Milky Way's halo. The stars in these streams still carry the chemical signatures of their birth galaxy. They still share similar orbital paths because they were all pulled from the same parent system, and they still move together roughly through space, even though the galaxy that held them together no longer exists. The most spectacular and best studied example of this process is happening right now, in real time, on astronomical scales. The Sagittarius Dwarf Elliptical Galaxy is a small galaxy that orbits the Milky Way at a distance of only about 70,000 light years from the galactic center. That might sound far, but for a satellite galaxy, it's dangerously close. The Sagittarius Dwarf is one of the closest known satellite galaxies of the Milky Way, and it's paying a terrible price for that proximity. The Milky Way's tidal forces have been tearing the Sagittarius dwarf apart for billions of years. Stars have been stripped from the dwarf galaxy on every close approach, pulled away by the difference in gravitational force between the near side and the far side of the small galaxy. Over time, these stripped stars have formed an enormous tidal stream that wraps completely around the Milky Way. The Sagittarius stream, as it's called, is one of the longest and most dramatic stellar streams in the galaxy. It stretches across the sky in a vast arc, a river of stolen stars that circles the entire Milky Way like a thread wrapped around a spool. The stream extends for over 1 million light years if you trace its total unwound length, looping around our galaxy multiple times. The discovery of the Sagittarius stream was a landmark moment in galactic astronomy. In 1994, astronomers Rodrigo E. Bartar, Mike Irwin, and Jerry Gilmore discovered the Sagittarius dwarf itself, which had been hidden behind the dense star fields of the galactic center. It was astonishing that a galaxy so close to us had gone undetected for so long, but the Sagittarius dwarf is small, faint, and positioned directly behind the brightest, most crowded part of the Milky Way's disk from our perspective. It was like trying to spot a dim candle behind a bonfire. Once the Sagittarius dwarf was found, astronomers began to map the distribution of its stars and quickly realized that the galaxy was being torn to shreds. Stars trailed away from it in both directions along its orbit, forming the enormous stream that had been hiding in plain sight in the data. The Sagittarius stream wraps around the Milky Way in a roughly polar orbit, meaning it passes over the top and bottom of the disk, rather than orbiting within the disk's plane. This is consistent with the random orbital directions we see in the halo. The stream's stars are now part of the halo, orbiting on paths that take them far above and below the disk, following the doomed track of their parent galaxy. The Sagittarius dwarf itself is still partially intact, though just barely. Its course still holds together, a dense clump of stars resisting the tidal forces that have stripped away most of its original population. But every time it completes another orbit around the Milky Way, more stars are pulled away. The galaxy is dying in slow motion. In a few billion years, it will be gone entirely, its remaining stars scattered across the halo, absorbed into the Milky Way, indistinguishable from the rest of the halo population except by their shared chemical signatures and orbital patterns. The globular cluster M54, one of the brightest globular clusters in the sky, is actually associated with the Sagittarius dwarf rather than the Milky Way itself. M54 sits near the core of the dying galaxy, and was likely one of the Sagittarius dwarf's own globular clusters, formed within it long ago. When the Sagittarius dwarf is finally consumed, M54 will become part of the Milky Way's collection of globular clusters, a stolen treasure claimed as spoils of galactic conquest. And astronomers believe this has happened before. Some of the globular clusters currently orbiting in the Milky Way's halo may not have formed in the Milky Way at all. They may have been captured from consumed dwarf galaxies, their original homeworlds long since destroyed. The Sagittarius stream is the most prominent example of a stellar stream in the Milky Way, but it's far from the only one. Astronomers have now identified dozens of stellar streams in the halo, each one the remnant of a different galaxy or star cluster that was captured and torn apart by the Milky Way's gravity over billions of years. These streams come in different sizes, different orientations, and different states of dissolution. Some are relatively young and well-defined, their stars still clustered tightly along a narrow track. Others are ancient and diffuse, their stars spread over such a large volume that the stream is barely distinguishable from the general halo population. The Palomar 5 stream, for example, is a narrow ribbon of stars trailing away from a dissolving globular cluster called Palomar 5. Unlike the Sagittarius stream, which comes from a dwarf galaxy, this stream is the result of a star cluster being slowly pulled apart by the Milky Way's tidal forces. Palomar 5 is losing stars from both sides, creating twin tails that stretch across more than 20 degrees of sky. In a few 100 million years, the cluster will be gone entirely, its stars dispersed into the halo. Another well-studied stream is the GD1 stream, a thin, coherent ribbon of stars stretching across about 63 degrees of the sky. This stream is thought to be the remnant of a globular cluster that was completely destroyed long ago. The cluster no longer exists as a recognizable object. It has been reduced entirely to a stream, a narrow trail of stars tracing out the ghost of an object that vanished perhaps billions of years ago. The stars are still there, still moving together on similar orbits, but the structure that once held them together is gone forever. Back in 1999, astronomer Armina Helmi identified a group of stars in the solar neighborhood that shared very similar orbital properties and chemical compositions despite being scattered across different parts of the sky. These stars, now called the Helmi streams, are thought to be the remnants of a dwarf galaxy that was consumed by the Milky Way between 6 and 9 billion years ago. The galaxy has been so thoroughly dissolved that its stars are spread across a vast volume of the halo, but their shared motions and chemistry betray their common origin. They're orphans, stars whose home galaxy was destroyed billions of years ago, now wandering through the halo, carrying the chemical fingerprints of a world that no longer exists. Each of these streams tells a story. Each one records the destruction of an independent stellar system, a galaxy or cluster that existed on its own, with its own stars and its own dynamics, before falling into the Milky Way's gravitational embrace and being torn apart. And the combined weight of all these streams, all these remnants, all these ghostly threads winding through the halo, tells a larger story about how the Milky Way itself was built. Our galaxy didn't form in pristine isolation. It grew, in part, by consuming its neighbors. It has been devouring smaller galaxies for billions of years, absorbing their stars into the halo, adding their mass to its own, growing larger and more massive with each cosmic meal. The halo is the record of this process. It's a graveyard of consumed galaxies, their stars still orbiting, still carrying the evidence of their origins, even though the galaxies themselves are gone. But the most dramatic revelation came from the Gaia spacecraft. As we touched on earlier, Gaia has measured the precise positions, distances, and motions of nearly 2 billion stars. This unprecedented dataset allowed astronomers to do something that had never been possible before. They could examine the detailed motions of millions of halo stars simultaneously, looking for patterns that would reveal the halo's hidden history. And what they found was staggering. In 2018, multiple research teams analyzing Gaia data independently came to the same conclusion. A huge fraction of the stars in the inner halo, the region of the halo closest to the disk, did not come from many small galaxies consumed over the Milky Way's lifetime. Instead, a large portion of the inner halo was deposited by a single enormous merger event that occurred roughly 8 to 11 billion years ago, A substantial galaxy, far larger than any of the small dwarfs being consumed today, had collided with and been absorbed by the Milky Way in a cataclysmic event that reshaped the entire galaxy. This ancient galaxy has been given several names by different research teams. It's sometimes called Gaia-Enceladus, after the giant of Greek mythology, because of the massive impact it had on the Milky Way. It's also called the Gaia sausage, a name coined by astronomer Vasily Beylokurov and colleagues because of the distinctive elongated shape its stars trace out in certain plots of velocity data, resembling a sausage. Today, astronomers often refer to the event as the Gaia-Enceladus sausage merger, acknowledging both naming conventions. The galaxy that merged with the Milky Way was not a tiny dwarf. It was a substantial system, estimated to have contained somewhere between a few 100 million and 1 billion stars, with a total mass, including dark matter, of roughly 10 billion times the mass of our Sun. That makes it comparable in size to the Large Magellanic Cloud, one of the Milky Way's largest current satellite galaxies. This was no minor snack. This was a major meal. The collision between the young Milky Way and this massive intruder would have been a transformative event, disrupting the disk, scattering stars in every direction, and depositing an enormous number of stars into the halo. The evidence for this merger is written in the motions of halo stars. Stars from the Gaia-Enceladus sausage merger share distinctive orbital properties. They tend to move on highly elongated, radial orbits, plunging toward the galactic center and then swinging back out again, rather than circling in roughly circular paths. This radial character is what produces the sausage shape in velocity plots. These stars also share a common range of chemical compositions, consistent with having formed in a single galaxy with its own history of chemical enrichment, distinct from the Milky Way's own chemical evolution. Their metallicities cluster in a particular range, and the ratios of specific elements in their atmospheres follow patterns that match formation in a separate, somewhat less massive galaxy. The Gaia-Enceladus sausage merger explains a huge amount about the inner halo's structure. Before this discovery, astronomers had puzzled over why the inner halo seemed so different from the outer halo in terms of the orbital properties and chemical compositions of its stars. Now the answer is clear. The inner halo is dominated by debris from this single massive merger, while the outer halo is built from the accumulated remnants of many smaller mergers, spread over billions of years. The galaxy's merger history is layered, like geological strata. The inner layers record the most violent, most transformative events. The outer layers record the quieter, ongoing accumulation of smaller galaxies over cosmic time. This discovery also revealed something profound about the Milky Way's own disk. Simulations of the Gaia-Enceladus sausage merger suggest that the collision would have severely disrupted whatever disk existed at the time. The young Milky Way's early disk may have been partially or completely destroyed by the impact. Its stars scattered into chaotic orbits, some of them joining the halo population. The disk we see today, the beautiful, organized spiral structure we explored earlier, would have reformed after the merger, growing from fresh gas that settled back into a flat, rotating plane once the violence subsided. In other words, the current disk is not the original disk. It's a second-generation disk, rebuilt after the most violent event in the Milky Way's history. The galaxy we know today rose from the wreckage of an ancient cosmic collision. Think about what this means for our understanding of the Milky Way. The calm, orderly spiral galaxy we live in, with its neat spiral arms and organized rotation, is the product of a catastrophic collision. Billions of years ago, two galaxies smashed together in an event that scattered stars across tens of thousands of light years, disrupted the existing galactic structure, and fundamentally altered the course of the Milky Way's evolution. And the evidence for this titanic event survived, preserved in the orbits and chemical compositions of halo stars for billions of years, waiting to be discovered by a spacecraft measuring the motions of stars with unprecedented precision. The field that studies all of this, that reads the history of the galaxy from the chemical and kinematic signatures of its stars, is called galactic archaeology. It's an extraordinarily apt name. Just as terrestrial archaeologists reconstruct past civilizations from fragments of pottery, tools, and buildings left behind in the Earth, galactic archaeologists reconstruct the Milky Way's past from the fragments of consumed galaxies left behind in the halo. Each stream of stars is an artifact. Each chemical signature is a clue. Each unusual orbital pattern is evidence of a past event that can be reconstructed through careful analysis. Galactic archaeology has revealed that the Milky Way has consumed at least 20 to 30 smaller galaxies over its lifetime, and probably more. The Sagittarius dwarf is being consumed right now. Gaia-Enceladus was consumed roughly 8 to 11 billion years ago. The Helmi streams record a merger from 6 to 9 billion years ago. Other identified merger remnants include structures called Sequoia, Kraken, and the Pontus merger, each representing a separate galaxy that fell into the Milky Way at different times and from different directions. Some of these were small, contributing only a modest number of stars to the halo. Others, like Gaia-Enceladus, were enormous, reshaping the galaxy's entire structure. Each consumed galaxy added its stars to the halo. Each one contributed its globular clusters, some of which still orbit as distinct objects today. Each one brought its own dark matter, adding to the Milky Way's total mass. Over billions of years, this cumulative process of merger and accretion built the halo into the vast, complex structure we observe today. The halo is not a simple, uniform shell. It's a layered, structured, dynamically rich record of billions of years of galactic history, with each layer telling the story of a different consumed galaxy. And this process hasn't stopped. The Milky Way is still consuming smaller galaxies. The Sagittarius dwarf is the most dramatic example, but there are others. The Large and Small Magellanic Clouds, the two largest satellite galaxies of the Milky Way, are interacting with our galaxy gravitationally and losing material. The Magellanic Stream, an enormous ribbon of hydrogen gas stretching across more than 100 degrees of sky, has been pulled from the Magellanic Clouds by the Milky Way's tidal forces. In a few billion years, the Magellanic Clouds themselves may be absorbed entirely, their stars joining the halo, their gas feeding new star formation in the disk. Dozens of other small dwarf galaxies orbit the Milky Way at various distances, caught in its gravitational field. Some of these show signs of tidal disruption, stretching and losing stars as they orbit. Over the next several billion years, many of them will likely be consumed, their stars adding yet another layer to the halo's already complex structure. The Milky Way is a predator. It has been eating smaller galaxies for as long as it has existed, and it will continue doing so for billions of years to come. But let's step back and think about what this means for the scale of the galaxy. Because the stellar streams in the halo don't just reveal the galaxy's violent history. They also trace out its physical extent. Streams from consumed galaxies can stretch for hundreds of thousands of light years, wrapping around the galaxy at enormous distances from the center. Some streams pass through regions of the halo that lie 200,000 or 300,000 light years from the galactic center, far beyond the edge of the bright disk. Their very existence at those distances proves that the Milky Way's gravitational influence, and therefore the Milky Way itself, extends to those distances. The galaxy's reach is not defined by where the disk ends, it's defined by where its gravity can still hold onto stars, and that boundary lies far, far beyond the spiral arms. The streams also reveal the shape and extent of the galaxy's dark matter halo, because the paths of streams are determined by the gravitational field they move through, and the gravitational field is dominated by dark matter. By carefully measuring the positions and motions of stars in a stream, astronomers can work backward to determine the gravitational field that shaped their orbits. This technique, called stream fitting, has become one of the most powerful tools for mapping the distribution of dark matter in the Milky Way. The streams are like test particles, tracing out the invisible landscape of gravity that surrounds our galaxy, revealing the presence and distribution of matter that emits no light and can't be seen directly. The picture that emerges from decades of study is one of a galaxy far more complex, far more violent, and far more extensive than the simple spiral image suggests. The Milky Way is not a neat, self-contained disk of stars orbiting peacefully in space. It's a gravitational empire that has been conquering and absorbing smaller systems for billions of years, building up an enormous halo of stolen stars, ancient clusters, and dark matter that extends many times farther than the disk in every direction. Every stream in the halo is evidence of conquest. Every ancient, metal-poor star on a wild orbit high above the disk is a displaced citizen of a galaxy that no longer exists. Every globular cluster that turns out to have chemical signatures inconsistent with formation in the Milky Way is a captured trophy from a consumed neighbor. The stellar halo is not a quiet, empty outskirt of the galaxy. It's the aftermath of billions of years of cosmic violence, preserved in the positions and motions of stars like wreckage, frozen in space. And our sun sits in the middle of all this history, 26,000 light years from the galactic center, embedded in the rebuilt disk, utterly unaware of the ancient catastrophes that shaped the galaxy around it. The Gaia-Enceladus sausage collision happened billions of years before the sun even existed. By the time our star formed from a collapsing cloud of gas 4.5 billion years ago, the wreckage of that merger had long since settled into the halo, the disk had reformed, and the galaxy had resumed its calm, orderly rotation. We were born into a galaxy that had already survived its most violent chapter, a galaxy that had been rebuilt from the debris of an ancient cataclysm. But the evidence is all around us, written in the stars of the halo, preserved in streams and shells and orbital patterns that astronomers are only now learning to read. The stellar halo is one of the greatest archives in the universe, a record of destruction and construction spanning billions of years, written not in words or symbols, but in the positions, motions, and compositions of individual stars scattered across hundreds of thousands of light years of space. And every time astronomers point a telescope at the halo and map another stream, identify another consumed galaxy's remnants, or trace another orbital pattern back to an ancient merger, they read another page in the Milky Way's autobiography. The galaxy we live in was built through violence. It grew by consuming others. Its halo is the proof. And that halo, stretching far beyond the bright disk into the ancient darkness of intergalactic space, is what makes the Milky Way so much larger, so much older, and so much more dramatic than the pretty spiral picture could ever suggest. The streams, the ghosts, the remnants of devoured galaxies, they all tell the same story. The Milky Way doesn't end where the bright disk fades from view. It keeps going, outward into a vast sphere of ancient light, carrying the memory of every galaxy it has ever consumed, holding onto their stars across distances that dwarf the disk in every direction. And there's still one more layer to this story. One more structure that extends even farther than the stellar halo, invisible and immense, defining the true boundary of our galaxy in a way that challenges everything we think we know about what a galaxy really is. We've traveled from the familiar bright disk into the vast, ancient stellar halo, and along the way we've discovered that the Milky Way is far larger than most people realize. The disk stretches about 100,000 light years across, but the stellar halo extends to 300,000 light years or more from the galactic center, enveloping the disk on all sides in an enormous sphere of ancient stars, globular clusters, and the ghostly remnants of consumed galaxies. That alone should change how you picture our galaxy. But the story doesn't stop there, because beyond the stellar halo, beyond the most distant stars astronomers can detect, there is yet another layer, one that is invisible to every telescope that has ever been built, yet contains the overwhelming majority of the galaxy's total mass. It defines the true extent and the real boundary of the Milky Way, and it forces us to completely rethink what the word galaxy actually means. This invisible layer is the dark matter halo. To understand the dark matter halo, we first need to understand dark matter itself. And this is one of the deepest mysteries in modern physics. We know dark matter exists. We know roughly how much of it there is. We know where it concentrates, but we don't know what it is. Not in any fundamental sense. We've never captured a particle of dark matter in a laboratory. We've never seen it directly. We've never been able to touch it, contain it, or study it up close. Everything we know about dark matter comes from observing its gravitational effects on the things we can see: stars, gas, galaxies, light itself, and working backward to deduce that something massive and invisible must be there. The story begins in the 1930s, when Swiss astronomer Fritz Zwicky was studying the Coma cluster, a large collection of galaxies about 320 million light years from Earth. Zwicky measured how fast the galaxies in the cluster were moving, and used those velocities to estimate the total mass of the cluster. The logic was straightforward. If the cluster is gravitationally bound, meaning its galaxies are orbiting each other rather than flying apart, then the total mass must be large enough to produce enough gravity to keep everything together. The faster the galaxies move, the more mass you need to hold them in. When Zwicky ran the numbers, he found something shocking. The galaxies were moving far too fast for the amount of visible matter in the cluster to hold them together. The visible mass, all the stars and gas he could see, accounted for only a small fraction of the mass needed to explain the observed velocities. Something else had to be there. Something massive and invisible, providing the extra gravity needed to keep the cluster intact. Zwicky called this unseen material dark matter, and for decades most astronomers either ignored or dismissed his finding. Then, in the 1960s and 1970s, American astronomer Vera Rubin and her colleague Kent Ford conducted a groundbreaking study of spiral galaxies. They measured how far stars orbit the centers of these galaxies at different distances from the center. According to the laws of gravity as we understand them, if most of a galaxy's mass is concentrated in the bright, visible center, then stars farther from the center should orbit more slowly, just as planets farther from the sun orbit more slowly in our solar system. Neptune moves much more slowly in its orbit than Mercury does, because Neptune is farther from the concentrated mass of the sun. But that's not what Rubin found. In galaxy after galaxy, she measured that stars far from the center were orbiting just as fast as stars close to the center. The rotation curves, as astronomers call them, were flat rather than declining. Stars at the outermost edges of visible galaxies were moving at speeds that should have flung them off into intergalactic space, if the only gravity holding them was from the visible stars and gas. Something unseen had to be providing enormous additional gravitational pull, not just at the center but extending far beyond the edges of the visible galaxy. Dutch astronomer Jan Oort had noticed similar discrepancies even earlier when studying the motions of stars in the Milky Way, finding more gravitational pull than the visible matter could explain. But it was Rubin's systematic work across many galaxies that made the case undeniable. Dark matter was real. It wasn't just in one cluster or one galaxy. It was everywhere, in every galaxy astronomers examined. And there was a lot of it. Far more dark matter than visible matter, by a wide margin. Today, our best measurements, primarily from observations of the cosmic microwave background radiation, the afterglow of the Big Bang, combined with surveys of the large-scale structure of the universe, tell us that ordinary matter, the stuff that makes up stars, planets, gas, dust, and you and me, constitutes only about 5% of the total energy content of the universe. Dark matter makes up about 27%. The remaining 68% is dark energy, a separate mystery that drives the accelerating expansion of the universe. But for our purposes tonight, the key number is this. Dark matter outweighs ordinary matter by a factor of roughly 5 to 1. For every kilogram of normal matter in the universe, there are about 5 kilograms of dark matter. And this ratio holds within galaxies as well. The Milky Way is no exception. The total mass of all the visible matter in our galaxy, all the stars in the disk, all the gas and dust, all the stellar remnants, all the stars in the halo, everything you could theoretically see with a powerful enough telescope, adds up to roughly 60 to 80 billion times the mass of our sun. That's a lot of mass. But the total mass of the Milky Way, including its dark matter, is estimated at between 1 trillion and 1.5 trillion solar masses. Dark matter accounts for roughly 90 to 95% of the galaxy's total mass. The visible Milky Way, everything we can see, every star and gas cloud and globular cluster, is less than 10% of the galaxy's total mass. The overwhelming majority of our galaxy is invisible. This dark matter is not concentrated in the disk. It doesn't follow the bright spiral structure. Instead, it forms an enormous, roughly spherical halo that extends far beyond both the disk and the stellar halo. The dark matter halo is the largest component of the Milky Way by every measure except star count. It's the most massive component, containing roughly 10 to 15 times more mass than all the visible matter combined. And it extends to the greatest distances, reaching out to approximately 600,000 light years from the galactic center, and possibly even farther, Estimates range from roughly 500,000 to over 800,000 light years, depending on the method used and the assumptions made. Let's absorb that number for a moment. 600,000 light years. The bright disk is 100,000 light years across. The stellar halo extends to about 300,000 light years from the center. The dark matter halo reaches roughly twice as far as that. The dark matter halo of the Milky Way is so large that it extends a significant fraction of the way to the Andromeda galaxy, which is about 2.5 million light years away. In fact, there's growing evidence that the dark matter halos of the Milky Way and Andromeda may already overlap. Their invisible outermost regions touching or intermingling in the vast space between the two galaxies. The merger between the Milky Way and Andromeda, predicted to occur in about 4.5 billion years based on the motions of their visible structures, may already be underway in some sense at the level of their dark matter halos. The dark matter halo isn't uniformly dense. Its density is highest near the center of the galaxy, and decreases steadily with distance. Near the galactic center, within the inner few thousand light years, dark matter is densely concentrated, though it's still less dense than the visible matter there. Farther out, the dark matter density drops, but it drops more slowly than the density of visible matter. This is why dark matter dominates at large distances. The visible galaxy thins out and essentially ends at the edge of the stellar halo, but the dark matter just keeps going, getting thinner and thinner, but never quite disappearing, extending out to enormous distances before finally becoming indistinguishable from the general dark matter background of intergalactic space. This raises a genuinely fascinating question. Where does the Milky Way end? If the galaxy is not just the disk, not just the stellar halo, but also this enormous invisible dark matter halo extending hundreds of thousands of light years into space, then what defines the galaxy's boundary? Where does the Milky Way stop and intergalactic space begin? The answer is that there is no sharp edge. The galaxy doesn't have a wall or a fence or a clearly defined border. Instead, it fades. The density of dark matter decreases smoothly with distance from the galactic center, getting thinner and thinner until it eventually blends into the background density of the universe. There's no abrupt cut-off, no sudden drop to zero. It's a gradual transition, like the way a city's suburbs thin out into countryside. There's no exact point where the city ends and the country begins. It just gradually becomes less urban. Astronomers handle this ambiguity by defining a conventional boundary called the Vir-Eol radius. This is the radius within which the average density of the galaxy's dark matter halo is a certain multiple of the average density of the universe as a whole. The Vir-Eol radius isn't a physical wall. It's a mathematical convention, a useful way to define where the galaxy is dense enough relative to its surroundings to be considered a distinct, gravitationally bound object. Beyond this radius, matter is no longer strongly bound to the galaxy. It's more influenced by the gravity of other nearby structures. For the Milky Way, the Vir-Eol radius is estimated to be roughly 600,000 light years, though this number has significant uncertainty. Some models place it closer to 500,000 light years, others push it toward 800,000 or even beyond. The uncertainty reflects how difficult it is to measure the mass distribution of an invisible substance at enormous distances from the galactic center. But regardless of the exact number, the implication is clear. The Milky Way, defined as the complete gravitationally bound structure including its dark matter halo, is not 100,000 light years across. It's more like 1.2 million light years across, measured from one side of the dark matter halo through the center to the other. That's roughly 12 times the diameter of the bright disk. 12 times. The familiar spiral, as beautiful and vast as it is, represents only the innermost, most luminous fraction of the galaxy's full extent. Let me paint a picture of the layered structure we've uncovered over these hours together, because seeing all the layers at once reveals the true architecture of the Milky Way in a way that no single layer can. At the center, there's the galactic bulge, a dense, roughly spherical concentration of old stars about 10,000 light years across, with a bar-shaped structure running through it. At the very core sits Sagittarius I star, the supermassive black hole with a mass of 4 million suns. Extending outward from the bulge is the thin disk, about 100,000 light years across and 1 to 2,000 light years thick. This is where the spiral arms are, where new stars form, where gas and dust concentrate, where our sun orbits, and where life arose on at least one rocky planet. The disk contains the vast majority of the galaxy's visible stars, and almost all of its ongoing star formation. Surrounding the disk on all sides is the stellar halo, a roughly spherical distribution of ancient, metal-poor stars and about 150 globular clusters. The stellar halo extends to at least 300,000 light years from the galactic center, possibly farther. It contains only about 1 to 2% of the galaxy's stars, but it occupies a volume vastly larger than the disk. It's laced with stellar streams, the remnants of consumed galaxies, and it preserves the record of the Milky Way's violent merger history stretching back over 13 billion years. And surrounding everything, extending far beyond even the most distant halo stars, is the dark matter halo. Invisible, massive, and enormous, it reaches to roughly 600,000 light years from the galactic center. It contains approximately 90% or more of the galaxy's total mass. It defines the true gravitational extent of the Milky Way and determines the orbits of everything within it, from disk stars to halo stars, to satellite galaxies, to the streams of destroyed dwarfs winding through the outer halo. Each layer is larger than the one before. Each layer is less visible than the one before. And each layer is more massive than the one inside it, at least until you reach the dark matter halo, which outweighs everything else combined. The galaxy, in its full extent, is a nested set of structures, like a series of Russian nesting dolls, except each outer doll is vastly larger and heavier than the inner ones, and the outermost doll is completely invisible. This layered structure fundamentally changes what it means to say you live in the Milky Way. When most people say they live in the Milky Way, they're thinking of the disk. They picture themselves inside a spiral galaxy about 100,000 light years across. And that's not wrong exactly. We do live in the disk. Our sun is a disk star, orbiting within the thin, flat plane of the spiral. But the disk is just the innermost visible layer. The galaxy extends far beyond it, in structures we can barely see, and in structures we can't see at all. Our sun is not just inside the disk, it's deep inside the stellar halo, which envelops the disk on all sides. And it's deep inside the dark matter halo, which envelops the stellar halo. We're embedded in layer after layer of galactic structure, most of which is invisible from our vantage point within the thin plane of the disk. Consider the satellite galaxies of the Milky Way. There are at least 50 known satellite galaxies, small dwarf galaxies that orbit within the Milky Way's gravitational influence. The Large Magellanic Cloud, the most prominent satellite, orbits about 160,000 light-years from the galactic center. The Small Magellanic Cloud is about 200,000 light-years away. Many of the smaller dwarf satellites are even farther, some orbiting at distances of 300,000 light-years or more. All of these satellite galaxies are inside the Milky Way's dark matter halo. They orbit within the galaxy, held by its gravity, even though they're far beyond the edge of the bright disk. Think about what this really means, because it's one of the most genuinely mind-bending implications of everything we've discussed tonight. When you look at the Magellanic Clouds from the southern hemisphere, you see what appear to be separate fuzzy patches in the night sky, clearly distinct from the band of the Milky Way, seemingly independent objects floating in their own region of space. They look like they're outside our galaxy. They look like neighbors, separate entities, other structures in the cosmos that happen to be nearby, but they're not outside, they're inside. The Large Magellanic Cloud, with its roughly 10 billion stars, its own star-forming regions, its own internal structure, is orbiting within the Milky Way. Not near it, within it. The same way the Moon orbits within Earth's gravitational domain, the Large Magellanic Cloud orbits within the Milky Way's dark matter halo. It's a galaxy inside a galaxy, an independent stellar system that happens to exist entirely within the boundaries of a much larger structure. And it's not just the Magellanic Clouds. Dozens of other dwarf galaxies, entire collections of millions or billions of stars, orbit within the Milky Way's dark matter halo at various distances. Some are so far from the disk that light from them takes hundreds of thousands of years to reach us, and yet they're inside our galaxy. They're part of the Milky Way's gravitational territory, captive systems held in orbit by the dark matter that surrounds them on all sides. The Milky Way contains other galaxies within itself. That sentence sounds almost paradoxical, but it's simply a consequence of how large the dark matter halo truly is. The galaxy is so much bigger than the disk that entire other galaxies fit inside it. This realization changes the map of our cosmic neighborhood. The Milky Way isn't a compact spiral floating in empty space with a few small companions nearby. It's a vast gravitational territory, over 1 million light-years across, with dozens of smaller galaxies orbiting inside its boundaries, held captive by its invisible, dark matter halo. Some of these captive galaxies are being actively destroyed, their stars stripped away into streams that wind through the halo. Others are still intact, orbiting peacefully for now, though many will eventually be consumed. The Milky Way is not just a galaxy, it's an empire, a gravitational domain that controls everything within roughly 600,000 light-years of its center. And this empire is still growing. We discussed how the Milky Way has consumed numerous smaller galaxies over its history, building up its stellar halo through billions of years of mergers. This process continues. The Sagittarius dwarf is being destroyed right now. The Magellanic Clouds are losing material. Other small dwarves show signs of tidal disruption. And in about 4.5 billion years, the Milky Way will merge with Andromeda, a galaxy even larger than itself, in the most dramatic event our galaxy will ever experience. The combined galaxy, sometimes called Milkomeda, will be a massive elliptical containing roughly 1.5 trillion stars. Its dark matter halo will be even larger than the Milky Way's current halo, extending to perhaps 1,000,000 light-years or more from the new combined center. But let's come back to the present, to tonight, to where we stand right now and what all of this means for how we see our galaxy. When you go outside on a dark, clear night and see that pale band of light stretching across the sky, you're seeing the disk. The thin, flat layer of hundreds of billions of stars, viewed from inside. That's the part of the galaxy that makes itself obvious. It's luminous. It's structured. It's beautiful. It's the part that earns the Milky Way its name, because it looks like a stream of milk poured across the darkness. But the galaxy doesn't end at the edges of that glowing band. Far from it. Surrounding that band, invisible to your eyes, extending in every direction far beyond the plane of the disk, is the stellar halo. Ancient stars, globular clusters, and the ghostly streams of consumed galaxies, all orbiting in a vast spherical cloud that stretches 300,000 light-years or more from the center. You can't see it. It's too sparse, too dim, too spread out, but it's there, all around you, above you and below you and far beyond the edges of the visible disk in every direction. And surrounding the stellar halo, extending twice as far again into space, is the dark matter halo. Invisible in every wavelength of light, detectable only through its gravitational grip on everything around it, containing more than 90% of the galaxy's total mass. It defines the true extent of the Milky Way and holds everything else together. Without it, the disk would fly apart. Without it, the stellar halo would dissipate. Without it, the satellite galaxies would drift away. The dark matter halo is the scaffold, the foundation, the invisible skeleton that gives the galaxy its shape and holds it together across more than 1,000,000 light-years of space. The Milky Way is not a 100,000 light-year spiral. It's a multi-layered, multi-component structure over 1,000,000 light-years across. It contains a bright, thin disk of young and middle-aged stars, a vast, spherical halo of ancient stars and consumed galaxies, and an even vaster, completely invisible halo of dark matter that outweighs everything else combined and extends far beyond the reach of any star. Think about what we called the Milky Way at the start of tonight's journey. A beautiful spiral, 100,000 light-years across. And think about what we know now. That spiral is just the most visible layer of something 12 times wider, 10 times more massive than its visible matter suggests, laced with the remnants of dozens of consumed galaxies, and embedded in an invisible structure so large it nearly touches the dark matter halo of the next galaxy over. The galaxy doesn't end where the bright disk fades from view. That was the premise we start with tonight, and now you understand why it's true in the deepest possible sense. The bright disk is where the galaxy is most obvious, most photogenic, most alive with star formation and light. But the galaxy extends far beyond that glow into ancient, sparse, invisible realms that dwarf the disk in volume and mass. The Milky Way is not what it appears to be in the pictures. It's much, much more. What we call the Milky Way in popular imagination is like seeing only the lit windows of a building at night and mistaking them for the entire structure. The windows are real. They're bright and they draw your eye. But behind them are floors you can't see, foundations buried in darkness, and ground stretching far beyond the glow. The building is vastly larger than the pattern of light suggests. You just have to know where to look and what to look for. Our sun sits inside the disk, 26,000 light-years from the center, orbiting quietly in a minor spiral arm. From here, we can see the band of the Milky Way stretching across the sky. We can see some of the closer globular clusters, ancient sentinels orbiting in the halo. We can detect, with our most sensitive instruments, the faint stars and streams in the halo that trace the galaxy's violent past. And we can infer, from the motions of everything around us, the presence of the invisible dark matter halo that defines the galaxy's true extent. We live inside a galaxy that is far grander, far older, and far more complex than most people will ever know. The bright disk is only the beginning. The true Milky Way is a structure of breathtaking scale, built through billions of years of cosmic evolution, accretion, and galactic cannibalism. Its layers tell the story of the universe itself, from the ancient halo stars that formed in the cosmos's infancy, to the dark matter framework that was laid down in the moments after the Big Bang. Every layer reveals another chapter. Every structure carries another memory. And tonight, the next time you look up and see that pale, familiar band of light stretched across the darkness, you'll know something most people don't. That beautiful glow is just the innermost, brightest fraction of a galaxy that extends far beyond what any eye can see. A galaxy whose true boundaries lie hundreds of thousands of light years beyond the last visible spiral arm. A galaxy wrapped in ancient starlight and held together by invisible matter, stretching across more than 1 million light years of space. The Milky Way doesn't end where you think, it barely begins there. And knowing that, truly understanding it, changes how you see that quiet band of light forever. It's not just a pretty streak across the sky. It's the glowing heart of something immense, something ancient, something still growing, still consuming, still reaching outward into the dark. You're inside it. You've always been inside it. And now you know just how far it reaches beyond that familiar glow. Above you, below you, in every direction, the galaxy extends outward through layers of ancient stars and invisible matter, through the ghostly remnants of devoured galaxies and the dark scaffolding that holds everything together, out to distances that dwarf the bright disk the way an ocean dwarfs a single island. And yet, this island is where you stand. This disk, this thin, flat, luminous structure is where the sun shines, where the earth turns, where life arose and looked upward and wondered what it was part of. Now you know. You're part of something far larger than the pictures ever showed you. A galaxy that doesn't end where the spiral fades from view, but keeps going. Outward and outward, ancient and invisible, vast beyond easy comprehension, holding onto stars and galaxies and dark matter across more than 1 million light years of space. That's the true scale of the Milky Way's stellar halo and the galaxy it reveals. Not a flat spiral 100,000 light years across, but a layered, spherical, still growing structure more than 10 times that size, carrying the memory of every galaxy it has ever consumed, bound together by matter we cannot see, stretching farther into the dark than most people will ever imagine. You can see it for what it really is. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep explorations of the cosmos. Sleep well tonight, knowing you live not in a small spiral, but in the glowing center of a vast, layered galaxy stretching over 1 million light years across. Ancient and still growing, far grander than any picture has ever shown. Good night.